So we have discussed a lot of sorting algorithms like bubble sort, merge sort, insertion sort, selection sort, heap sort. So there is one more sorting algorithm remaining. So that was quick sort. So let's discuss quick sort in this lecture. Okay. So quick sort is another comparison based sorting algorithm. Till now we have discussed what is comparison based sorting algorithm. So in comparison based sorting algorithm, what we will do? We compare the elements, right? We compare the elements. So quicksort is another comparison based sorting algorithm. And in quicksort, we use partition algorithm. Like in merge sort, we use merge algorithm, right? So majority task was done by merge algorithm only. Like merge sort also, we have partition algorithm in quicksort. So in quicksort, we use partition algorithm. Now, how partition algorithm works? So we choose an element as pivot, right? What does pivot means? Pivot means that which divides the array or which divides our data structure in two parts. Okay, so we choose an element as pivot. Now we perform the partition algorithm to the pivot element. So the idea behind choosing the pivot element is because we want to put the pivot element at its correct position, right? So we will see with an example, but our idea is to choose the element as pivot and put it in the correct position. What does it mean? It means that we'll put the element in correct position, and before that everything will be smaller, and after that everything will be larger than the pivot element. Okay, so we will see an example. Now what does it mean? The right side element will be greater than pivot element, and the left side element will be smaller than or equals to pivot element. Okay, so that's I have written the left side element of the pivot element will be less than or equals to pivot element, and the right side element will be greater than pivot element, right? Now when we choose the pivot element, so left side will be smaller elements and right side will be larger elements, but they also need not to be in the sorted order. Okay, so we will see an example. Now it is considered as in place algorithm. Quicksort is considered in place algorithm, that we will see in an example, and it is not stable. What does it mean? It means that the order of repeating elements will change or can change. Okay, now let's come to pivot selection. So we can select pivot in many ways. Okay, whatever way you want. Select first element as pivot, select last element as pivot, select random element as pivot, select median as pivot. So pivot is nothing but selecting an element from the array and putting it in the correct position. Okay, so we will see this first element as a pivot and we will see last element as a pivot. Okay, so we will do quicksort using these two methods, right? So quicksort code will be same, but the partition algorithm will be changed. Okay, the partition algorithm will work according to the pivot selection. Okay, so let's see, if we select first element as pivot, then how we can do the partition algorithm. Okay, so first start with the first element as pivot. So let's take the example. So let's say we have array like 4, 5, 2, 1, 3, 6, 7. Okay, now if I choose first element as pivot, I can choose first element as pivot. Okay, I can choose last element as pivot. I can choose this middle element as pivot. I can choose median element as pivot. So what is median? Median will be 3 or 4. Okay, so or I can choose any random element as pivot. I can choose this as pivot. Okay, now the idea is putting the pivot at its correct position. Okay, so let's take this example. Now if I select 6 as pivot, so this is as pivot. Now I want to put it in the correct position. So let's say I put it in the correct position. So before it, everything will be smaller than or equals to 6, or after this everything will be greater than 6. Okay, right? So in the right side we have greater element, and in the left side we have smaller or equals element. So let's say I take 6 in the correct position. So what will be the 6 correct position? Before 6 we can have 1, 2, 3, 4, 5. and after 6 we can have only one element, that is 7. Okay, so these elements need not to be in the correct order. Okay, these can be in any random order, but our 6 will be positioned at the correct position. Okay, so every time I will take a pivot element and put it in the correct position. Now after 6 we have only one element. Okay, so if we have only one element, then it will be sorted, right? So after putting 6 into the correct position, we also need to correct the left side also and the right side also. So we need to sort the left side and right side also. So what I will do, I will again choose the pivot from the left side. So let's say I choose first element as the pivot from this portion. Okay, this is the left portion. So I will choose pivot from left portion. Okay, this can be in any order, right? 1 2 3 4 5 can be in any order. So for example, I am taking it. Okay, so let's say I choose 1 as a pivot. So what will happen? I will put it in the correct position. So before 1 nothing will be there, right? And after 1 2 3 4 5 will be there, and 1 is our pivot. Okay, so 1 is our pivot. So before 1 smaller than 1 will be there, and after 1 larger than 1 will be there. Okay, these can be in any order, right? So we need to sort them. Okay, so we need to sort them. Okay, so again we will choose 2 as pivot, then again let's say this will be nothing, and this will be 3 4 5, then again we will choose 3 as pivot. Okay, then again we'll choose first element as pivot. So we will keep on doing until my array gets sorted. Okay, so that's the idea. Now let's see how we can do the idea is very simple, that we will put the pivot in the correct position. Okay, so let's say if I choose 2 as a pivot, so 2 correct position is second, right? So we are taking element 1 2 3 4 5 6 7, right? So 2 will be in second position in the correct position. So the correct position of 2 is second. So if I choose 2 as a pivot, then I will make sure that 2 will be in the second position after my partition algorithm. Okay, so I will design my partition algorithm according to my pivot selection. Okay, so in this example we are selecting first element as pivot. Okay, so let's continue with this approach only. Okay, now let's take this array. Okay, and we will try to sort it using our partition algorithm and our quick sort. Okay, so let's select this as pivot. Okay, so let's select this as pivot. So this is our pivot, and let's start from this one. So this is our start index and this is our ending index, right? So start index will be the first element and the ending index will be the last element in the beginning. Okay, now take it as I. Okay, so take first element as I. Okay, and take it as pivot also. So pivot will store the first element. Okay, so this will be nothing but array of start, right? So it will contain 6. Now our I will store the index. Okay, so let's store the index. So our index is start. Okay, so initially we will take this. Now take J, run a loop from here to here. Okay, so I am selecting first element as pivot and I will run a loop from second element to my last element initially. Okay, so the idea is I will run the loop from the next element. So I am taking I as first element, so I will run the J loop from next element. So take this as J. Okay, so our J will start from I plus 1, right? And I will run it till the end. So J will be run till end. Okay, so I will run a loop from here to end, and I will check those elements which are less than pivot. I will keep them in the left side. How I will keep them in the left side? Let's see. So let's compare 3 and 6. 3 is less than 6, right? So what I will do, I will increment the index of I. Okay, so I will be here and J is already here. So I will swap array of I with array of J. So I will swap 3 with 3. right? Now I will increment my j count. So j will be here now. Okay, so I will point to first index and j will point to second index. Now compare 2. 2 is less than pivot, right? I will again increment I and swap array of I with array of j. Okay, so again increment I. So I will be here, j will be here. I will again swap 2 with 2. Okay, now increment j. Okay, so now my j will be this. Now check if array at j position is less than my pivot element. Yes. So what I will do, I will again increment my I count and again swap array of I with array of j. So it will be 1. Okay. So what I am doing, I am basically collecting all the smallest element then pivot in the one position. Okay. And then at the end what I will do, I will swap the pivot element in the correct position. Okay. So till now what I am doing, I am finding the correct position of pivot element. Okay. So I will again increment my j. So my j will be here. Okay. And I will compare, is 4 less than my pivot element? Yes. So I will again first increment my I count and then do a swap. Okay, so it will be 4. Now again what I will do, I will increment my j. Okay, so let's say j is here. Now I will again compare. 5 is less than my pivot element? Yes. Okay, so I will again increment my I count. So I will be here, right? And I will swap array of I with array of j. So it will be 5 only. Now the interesting case, I will again move j. So my j will be here, right? Now I will check 7 is less than my pivot element? No. Okay, so I move j forward. So now j reaches to the end of the array. Okay, so the inner loop, this loop is ended. So we got all the elements less than pivot element at one place here, right? So I got all the elements less than my pivot element at one position. Okay, now after this loop ends, what I will do, I will swap my array of I with array at start. Okay, because start contains the pivot element. So I will swap the positions of array of start with array of I, because I is pointing to the correct position of the pivot element. So let's swap this. Let's swap 5 and 6. Okay, so this position is the correct position of our pivot element. So I holds the correct position of our pivot element. So let's swap this. So this will be 6 and this will be 5, right? So before 6 all the elements are less than 6, and after 6 all the elements are greater than 6. Okay, so after first iteration the array will look like, so after first partition our array will look like this. Now 6 is at correct position, but this part is not sorted and this part is also not sorted. Let's say it's not sorted, right? We have only one element, that's why it seems like sorting. So it can happen that left part will not sorted and right part will not sorted. So we will sort it again. Okay, so how we'll sort it? We will again consider this array, right? We will again consider this array and we will again take a pivot element and then we will again divide and put the pivot in the correct position. So how we will do this? So let's say this is 6. Now left of 6 we have 5, 3, 2, 1, 4, and at the right we have 7. Okay, so now let's sort this one. So let's say this is start, okay, and this is end, right? Now again take this as I and take this as pivot element. So pivot will be 5, okay, and take j is 3, right? So I and j stores the index. Okay, so array of I will be 5 and array of j will be 3, right? So we have taken 5 as a pivot. Now again what I will do, I will run a loop. from j till n. So I will compare each element with the pivot element. Okay, I will compare each element with the pivot element and put my 5 at correct position. Okay, so put my pivot element at correct position. So what will be the correct position of 5? See, 3 is less than 5, 2 is less than 5, 1 is less than 5, 4 is less than 5. So the correct position of 5 is the last position. Okay, so it should become in the last position. Let's see how we can do this. So let's compare. This is our I, this is our j. Let's compare. Is 3 is less than pivot element? Yes. So increment the I and swap the array I with array j. Okay, so swap it with 3. Now increment the j. Now again compare. 2 is less than 5? Yes. So 2 is less than pivot element. That means it should also move. So we should put I in the correct position. So again move I. Observe the movement of I. I is here. That means it got the 2 elements which are lesser than the pivot element. Okay. So we got 2 elements which is less than the pivot elements. So which says that the correct position of our pivot element should be 3 till now. Okay. So I will again swap it with 2, right? I am swapping array I with array j. Now again move this j loop. Okay, so now j is pointing here. Now again compare. Array of j is less than my pivot element? Yes. So I will first update my I and then do a swap. Okay, so let's write here I and swap it with array of I and array of j. Okay, so it will be 1. Now I will move my j forward. Okay, so let's move it to here. So j is here. So compare 4. 4 is less than my pivot element? Yes, because 4 is less than 5, right? So first move I. What does it mean? It means that the correct position of 5 should be this one. Okay, now swap this. So I will swap this with 4. Okay, so till now basically it's a coincidence that array of I and array of j are at same index. Okay, so every time it should not be in the same index. Now I will move j. So now my j will point here. Okay, so I have reached to the end of the array. So my j loop will end here. Now at the end we have 5 here, right? We have pivot element here and we have 4 here. So the correct position of my pivot element is at my ith index. So what I will do, I will swap the element at my start index with the element at my I index. Okay, so I will write swap array of I with my array of start, because array of start contains the pivot element, right? So this is nothing but pivot element. Okay, so what I will do, I will swap them. So it will be 5 and it will be 4. So this will be 4. Okay, so 5 got its correct position. Now move forward. Okay, so after this 5 is reached to the correct position. Okay, so after 5 we have nothing, and before 5 we have 4, 3, 2, 1, right? So what I will do, I will again take my 4 as my pivot element. So let's take it as pivot element. So it will be pivot equals to 4 and I equals to array of index 0. Okay, so this is the start and this is end. So I will store start and I will start j from my this index. So j will contain 1. Okay, j will contain 1. Now I will again compare. So in this time also, every time we will swap them. Okay, and at the end 4 will come here. So after this loop, what will happen? Every time, see in this case, in this subtree, every time my pivot will shift to the last element, because every time it is greater. So after this what will happen? I'm quickly doing this, right? So I'm quickly doing this because I hope you understood it. So 4 will here. Okay, so after 4 we have nothing, and before 4 we will have 3 2 1. Okay, so now also I will again take this as pivot, and I will run a loop from my another index. Okay, so I will run a loop from j equals to 1. Okay, same case we are doing again and again. Okay, so this will give us a 3 will come here. Okay, so after 3 we have nothing, and before 3 we will have 2 and 1. Okay, now if we come to this case, so this will also, we will take 2 as pivot, and after 2 we will have nothing, and before 2 we will have 1. Okay, so when we reach to 1, okay, when we reach to this element where my start is equals to my end, that means we have only one element. So if there is only one element, do we need to sort? No, right? So when start will equals to end, then what I will do, I will simply return this, right? Because there is only one element. So when I reach to this case, I will simply return. Okay, so let's revise it. Okay, so this subtree is solved. Now come to this subtree, this after 6. So after 6 come to 7. Okay, so again we have only one element, right? So what I will do, in this case my start is equals to my end, right? So this is the start also, this is end also. So I will simply return it because we have only one element. So it will be in correct position, right? So it is already in the correct position. So I will return it. Now let's quickly summarize it. So first 6 will be at correct position. Then we will come to the left subtree. So in left subtree 5 will be at correct position. Okay. Then from here 4 will be in correct position. Then from here 3 will be in correct position. Then from here 2 will be in correct position. Then from here 1 will be in correct position. Okay, and from here 7 will be in correct position. Okay, so my partition algorithm, this is nothing but our partition algorithm. Let's name it as partition algorithm, right? Partition. So if we observe carefully what we are doing, in single time we are putting one element at correct position. So every time we are putting one element at correct position. Okay, so my partition algorithm will take the time complexity of order of n, right? It will run till order of n. Okay, that is the worst case, right? So my partition algorithm will run for n times. Okay, so this is the heart and soul of quicksort. If you understand partition algorithm, you understand the quicksort algorithm. Okay, so let's write in our pseudocode. So in pseudocode, what I am doing, first I am taking my partition. Okay, so partition algorithm will run for from 0 till, let's say we have array. Okay, so its first index is 0 and last index will be n minus 1. Okay, so it will be run till 0 to n minus 1, right? So this will be a partition algorithm. So in partition algorithm, what I will give? I will give my pivot element also. Okay, so let's say I'm giving pivot element. So in this case, I am giving 0 index, right? So 0 is my pivot element. Or what we can do, we can simply find out in the array also. So no need to give pivot externally. Okay, we can find it in the array itself. So my first element will be pivot element. Okay, so this is our partition algorithm, right? It will run from start to end. Now what I'm doing, I'm taking, let's say I am taking my pivot element. So my pivot element is what? My array of start. Okay, and I will take a index I. So I index will store the starting index. Okay, initially it is 0, so it will store 0. So it will store 0, it will store array of 0, right? But this starting and ending index will keep on changing. Okay, so quicksort will handle this, right? Initially quicksort will pass 0 and n minus 1 as start and ending index. Okay, so initially start is 0 and ending is n minus 1 because we want to do partition for whole array, right? Initially we are passing whole array for partition algorithm. Now I will run a loop. Okay, so I will take j, and j will start from I plus 1. Okay, so if I am taking this element as I, j loop will start from next index. So j will run till my end. Okay, and I will keep on incrementing the j. So every time what I will do, every time for every element, what I will do, I will check if my array of j, if array of j is less than my pivot element. So what I will do, I will swap. I will first increment my I, okay, and I will swap. I will swap what? I will swap my array of j with array of I. Okay, that's what we will do. Now this whole loop will keep on running and will keep on putting the element less than my pivot element in the one bunch. Okay, so this loop will keep on putting the whole elements which are less than my pivot element at one end. Okay, so at the end I will be the correct position for our pivot element. Okay, so at the end what I will do, after running this for loop, what I will do, I will swap my array of I with my start index. Okay, because start index contains the pivot element, right? So you can write pivot here also, but if you write pivot, then it will not do changes in the original array. So I want to do changes in the original array, so I will pass it by reference. Okay, that we will see in the code. So I will pass it by reference because it is not using any extra space. Whatever we are doing in place. Okay, in the original array. So we use reference for original array. We use reference to put changes in the original array. Okay, so by reference we will do changes in the original array. So this is our partition algorithm, and the time complexity of partition algorithm is order of n. So partition algorithm takes order of n time. Why? Because we are running this loop, right? We are running this loop. Okay, so this loop runs almost for n times. Okay, for worst case we say almost of n times. So partition algorithms take how much time? It takes order of n time, right? It takes order of n times. So I hope partition algorithm is clear to you. Now how we do quick sort. So let's see this. So let's say this is quick sort. Okay, this is quick sort, and in quick sort we are passing the array. So let's say we are taking 0 and n minus 1, okay, as the index. Now in quick sort, first I will find my pivot element. Okay, so how do I find the pivot element? I will call the partition algorithm. So I'll call the partition algorithm for start and end, right? I'll call the partition algorithm for start and end. Okay, and I will pass the array here. Now after finding the pivot element, what I will do, I will again run a quick sort for how many elements? For the left side and right side elements. So I will run a quick sort for left side elements. So now this is a pivot element. Okay, so it will give us the index. It will give us the index of pivot element. Okay, so I will run the quick sort algorithm for start till my pivot minus 1. Okay, let's say 4, 5, 1, 2, these are our elements. Okay, and I am choosing 4 as our pivot element. So what is the correct position of 4? So 4 will be placed here. So after 4 we will have 5, and before 4 we will have 1, 2. Okay, so let's say what is the index of 4? The index of 4 is 2. Okay, 0, 1, 2, 3. So I will run the quick sort for pivot minus 1 elements for left side, and I will run a quick sort from pivot plus 1 till end for the right side. Okay, so I will run a quick sort for pivot minus 1 element for left hand side. So my quick sort will run for pivot minus 1. Okay, this is for left side, right? And we'll pass the array here also. Now this recursive function will take care of left side elements. Now we'll pass for right side elements. Okay, so my right side element will start from my pivot plus 1 index, and it will run till my end. Okay, so this will take care of my right side, right? So first what I will do, I will find the pivot. Okay, so by partition algorithm I will get the correct position of my pivot, and partition algorithm will put the pivot at correct position. Partition algorithm will put the pivot at correct position. Okay, but my left and my right will not be in sorted order. So for sorting left, I will run a quick shot for left side, and for right I will run a quick shot for right side. So again quick sort will run, again partition algorithm will call. Okay, now second time my start will remain same for left side, and end will be pivot -1. Okay, and for right side my start will change, my start will be pivot +1, and end will remain same. Okay, so again partition algorithm will be called, so it will called. Okay, it will keep on calling. Now what if we reach to one element? So if my start is equals to end, so I can write if my start, usually we write greater than equals to end. Okay, so to handle the case, to handle the array out of one case, so if my start is greater than equals to end, that means what? That means we have only one element, so we will simply return. Okay, so let's say in the array we have only one element. Let's say we have one. What will you sort? Nothing, right? So this is the pseudocode for quick sort. I hope you understood it. Now if we write the recurrence relation, okay, so let's say we write the recurrence relation. So we have discussed that partition algorithm takes order of n times. Okay, this take order of n times. Let's discuss the time complexity. So what will the time complexity? So let's write it in the form of recurrence relation. Okay, so let's say we have n elements, right? And n time will be taken by my partition algorithm, right? That is fixed. Now in best case what can happen? Let's say we have array like 3 2 1 4 5. Okay, and I choose 3 as the pivot element. So after one partition 3 will be here, right? So on the left of 3 I will have 2 and 1 in any order, and on the right we have 4 or 5 in any order, right? Now again I will choose 2. Okay, so on the left we will have 1, and on the right we will have nothing. And similarly if we choose 4, so on the left we will have what? We will have nothing, and on the right we will have 5. Okay, so in best case what can happen? That every time when we choose our pivot, so it divides the array in two equal parts, almost two equal parts. Okay, so in best case what can happen? Let's say in best case what can happen? My partition algorithm divides the array in two equal halves. Okay, that we have seen. If we take the 3, so 3 will divide 1 2 here, 4 5 here, right? If we take more elements, let's say 1 2 3 4 5 6 7 8 9 10. Okay, so let's say my partition algorithms divide 4 here, 1 2 3 4 here, and 6 7 8 9 here. And let's say I again choose 3 as a pivot element. So my partition algorithm divide 1 2 here, 4 here. Let's say I choose 8 as a pivot element. So my partition algorithm will divide 6 7 here and 9 here. So it divides my array in two equal halves, right? So this can be the best case of our quick sort. Okay, so let's rub this. So best case can be when our partition algorithm divide the array in two equal halves. So let's say we have n elements. So my partition element divide it in the two equal halves. Okay, so it will be 2t n by 2. So this can be the recurrence relation for the best case. Okay, and it will be nothing but tn equals to 2tn by 2 plus n. Okay, so this is similar to the merge sort, right? So if you find it using Master's theorem, okay, so solve it using Master theorem. Okay, so after solving it using Master theorem, the time complexity will give is order of n log n. Okay, so the time complexity it will give is order of n log n, right? So this will be the time complexity of quick sort in best case. Okay, in average case also this will be n log n. Now let's discuss the worst case. Okay, so let's see our previous example. So in this example, if you see carefully here, after sorting 6, we had elements 4, 3, 2, 1. Okay, so when we are choosing 4, okay, every time when we are choosing the pivot element, our array got inclined in one side only. Okay, so here this side, right side is empty and left side contain all the elements. So in this case, when I choose 4 as a pivot element, my left side got all the elements and my right side got empty. So again, when I choose 3 as a pivot element, so right side got empty and left side, all the elements were on right side. So this is the worst case. This is the worst case of quick sort, because every time we need to take one pivot element. Okay, so this will run for this, the height will be almost n. Okay, so the height will be almost n in worst case. So let's discuss it. So let's discuss the worst case with the help of our recurrence relation. Okay, recurrence relation. So we have, let's say, n elements. Okay, and every time my pivot divides my elements in n minus 1 elements. So every time my quick sort is divided into n minus 1 elements. Okay, so every time my partition algorithm divides it into n minus 1 elements. Okay, so 5, 4, 3, 2, 1. So let's say we have 5, 4, 3, 2, 1. Okay, so if you take 5 as a pivot element, then on the right we will have nothing, on the left we will have 4, 3, 2, 1. Similarly, if you take 4 as a pivot element, then right will have nothing, left will have 3, 2, 1. Okay, similarly, if you take 3, then every time it is inclined towards left side. Okay, so similarly, if you take 1, 2, 3, 4, 5, and you take 1 as a pivot element, so it will be inclined towards right side. So if the tree is inclined towards left or towards right, then it will be the worst case. Okay, so let's discuss it. So the time complexity of partition will be n only. Okay, and order of one time will be taken by pivot selection. Okay, so every time we are selecting my pivot, so it will be order of 1. So when you solve this, the time complexity will be order of n square in worst case. Because every time you are calling the tree for every element. Okay, so the tree will be inclined in one side only. So if the tree is inclined in one side only, then it will be worst case. So let's discuss the time complexity. So in best case, time complexity will be order of n log n, and in worst case the time complexity will be order of n squares. Okay, and in average case it is considered as order of n log n only. Okay, so this was the time complexity for all the cases. Now what will be the space complexity? We are not using any extra space, so it will be order of 1. Okay, and I am not including the recursive space. Okay, so order of 1 will be the space complexity. Okay, so this was all about the quick sort. Now to be generic, what will be the recurrence relation? So the recurrence relation will be something like T of n minus k plus T of k minus 1 plus order of n. Okay, so let's say k is our pivot index. Okay, so T minus k, this will be for right half and this will be for left half. On the left half we will have k minus 1 elements, and on the right we will have n minus k elements. So this is the generic recurrence relation for quick sort. Okay, so this is a generic recurrence relation for quick sort. I have included all these in my notes. Okay, so if you refer my notes, it will be very clear to you. So in this example we had taken first element as the pivot. Now what if you take last element as a pivot? If you take last element as a pivot, okay, so what will happen? I am writing a pseudo code for it. Okay, and you will code it, right? I'm writing a pseudocode for it. So if you select, let's say 5 4 3 2 1, what will happen if you select last element as a pivot? Last element as a pivot. Okay, so this is our pseudocode for when I'm selecting last element as the pivot. Okay, so what I will do, I will take I as the first element and P pivot as the last element, and I will start J from here. So I will run my G loop from 0 to n minus 1. Okay, so every time what I will do, I will check whether my element is less than my pivot element or not. Okay, so I will check if my element is less than pivot element, I will keep swapping, and after swapping I will increment my I. Okay, so in the first case, when I am taking first element as pivot, I was first incrementing the index and then swapping. In this case, I will first swap the elements and then increment my I, and my I stores the my I holds the correct position of pivot element, holds the correct position of pivot element, right? So again, after this loop ends, I will swap my array I and array pivot. Okay, so same as when I'm taking first element as pivot. Okay, a little bit changes. So you can take this also and write your partition algorithm using last element as a pivot. Okay, so the time complexity will remain same. Okay, all things, everything will remain same. It's just that you are changing the way of pivot selection. Okay, so you can take first element as pivot, you can take last element as pivot. So this was all about quicksort, and let's code it in the Visual Studio Code. Okay, so let's write the code for quicksort. Let's call our quicksort here, quicksort, and I will pass my array. I will pass my starting index as 0. I will pass my ending index as n minus 1. Okay, now I will create a function, quicksort. Okay, quicksort. I will pass my array and I will name it as start. My start will contain 0. I will pass my end will contain n minus 1. And first I will check if my start is greater than or equals to end. That means we only have one element, so we will return it from here only, right? Otherwise what I will do, I will calculate my pivot. Okay, so let's name it as pivot, and I will call my partition algorithm. So partition algorithm will call for my array, and I will pass my start and I will pass my end here. Okay, now my partition algorithm will put the pivot element at correct position. Okay, so I am taking first element as my pivot element, so that will be in the partition algorithm. Now I will call my quicksort for left side, so I will call it for start will remain same and end will be my pivot minus 1, right? This is for left side. Okay, and for right side what I will do, I will call my quicksort function for array, and my start will be pivot plus 1. My end will remain same. Okay, so this is for right side elements. Okay, so I have called for left, I have called for right, and I find out the partition. So let's create the partition algorithm, which is the most important in our quicksort. So partition algorithm will return me the index of the correct index of the pivot. So let's take it as int. Let's take a partition. Okay, and let's take the array. Let's take the starting index. Okay, let's take the ending index. Okay, so in partition algorithm, what I will do, first I will take my pivot as my array of start, and I will take int I will contain the index of start, and I will run a loop. Okay, So I will run a loop for int j. J will be start from second index. So it will be I plus 1. J is smaller than equals to end j plus plus. And every time for every element, what I will do, I will check if array of j is less than my pivot element, right? So if it is less than my pivot element, then what I will do, I will swap value at index j and value at index. Okay, so first I will increment my I also. Okay, so before swapping, I will increment my I, and now I will swap with I. Okay, so this will keep on doing. Now after this, what I will do, after my for loop, I will swap my values. I will swap my values at my ith index with my start index, because start contains the pivot. Okay, this will be by reference. Okay, so this is about partition. Now is it correct? Okay, so now I will return my I, right? Okay, so this will be start. Sorry, my bad. This will be start. Okay, I will start from second index. So because i's keep on changing. Okay, so that will affect my j loop. Initially I and start are same, but i's keep on changing. So okay, so this will be j, not I, right? Now let's see if there is any error. Partition start, I will start arrays starting from start plus 1 and okay, and let's move this. Okay, let's run this. See 1 2 3 4 5. Let's see if I take some more elements. Let's say 9 comma 91 comma 23 comma 58 comma. Okay, now run this. 1 2 2 3 4 5 5 23 23 34 and okay, so all the elements are in sorted order. So this is how my quicksort works. So if you take last element as pivot, you can write your code for pivot element. Okay, you can write your code for last pivot element. So everything remains same. Your pivot will be changed and your for loop modification will be changed. Okay, quicksort function will remain same. Okay, quicksort will be same, but your partition algorithm will modify. So this is all about quicksort, and we have discussed time complexity, space complexity, recurrence relation. Okay, best case, worst case. Now this is all about this lecture also. So we have discussed all the sorting algorithms, we have discussed all the C++ STL functions which you will need in the future, and this is all about this lecture. Meet you in next lecture. Till then, bye bye, take care. Okay.